Another important method helping us to calculate the volume is using cylindrical shell method. In that case, when you are basically rotating your function, which in this case is this function here, along y-axis, you can basically build some cylinders and calculate the volume of those cylinders, add them all together to find the volume of this new object. So consider you have your function f and you start rotating it about y-axis. If we look at this cylinder, you basically see you have a circumference of 2 pi x, which is the circumference of this circular base. You have a thickness delta x, and you have a height f of x. The circumference is 2 pi x times the height, which is f of x. The thickness is delta x. When you take the limit, it becomes dx. And then you take the definite integral, and it gives you the volume using the shell method. Very good. Now, I expect you to ask, what if we have the region bounded between two functions like f of x and g of x, and we start rotating this about y-axis? Then, how do we calculate the volume of these small shells? The volume of these small shells is basically 2 pi x f of x minus g of x, and then you see x sub k star and x sub k star both here and also here. It's basically a representative value, and delta x is the thickness. Now, as you remember, if you take the limit of the Riemann sum, this is basically the definite integral of 2 pi, the integral of radius times the height of the shell. Delta x limit becomes dx, and x ranges between a to b, which in turn can be written as 2 pi, the definite integral of x, f of x minus g of x, dx, f of x minus g of x is basically the height of the shell. And then you have 2 pi x, which is the circumference, and delta x or dx, basically the thickness. Let's go over one example together. The region bounded by the curve y equals to square root of x, the x-axis, and the line x equals to 4. It is revolved about the y-axis to generate a solid. We are interested in finding the volume of this solid. Okay, what's the visualization look like? You have y equals to square root of x, bounded by x-axis, and the vertical line x equals to 4. When you start rotating this about y-axis, you can easily use the method of shell. In that case, the height of the shell is the distance between the function square root of x and x-axis, so you get square root of x minus 0 or just square root of x. You have the interval of integration between 0 to 4, and once you rotate this, this is the object that you're creating, and you can use the cylinder to calculate the volume of this object. So remember the formula. The volume using cylindrical shell is the definite integral of 2 pi, the radius of the shell, times the height of the shell. And again, delta x is basically the thickness of your cylinder. When you're taking the limit of delta x, b minus a divided by n as n goes to infinity, you create dx. In turns, it is equal to definite integral 0 to 4, 2 pi, the shell radius. It's located on x-axis, right? Times the height, which is located on square root of x, times dx, which is equal to 2 pi, definite integral of x to 3/2, x to the first power times x to a half gives you x to 3/2 dx, and then it is in terms, following the formula for the power u to the n du, which is u to power n plus 1 divided by n plus 1 plus constant of integration. We're applying the same thing here. N in this case is 3/2. It becomes 2 pi, 2/5, x to power 5 over 2, and x ranges between 0 to 4. It is equal to 128 pi divided by 5. So again, when you're asking to calculate the volume of an object rotated about x-axis, rotated about y-axis, you can go back and use different methods. We're introducing this method using the cylindrical shell method because it makes the calculation easier for us. On the exam, on the homework, if it doesn't specify which method to use, you can freely choose between the method of shell, or you can use disk method or washer method to calculate the volume of the solid of revolution with respect to x-axis or y-axis or given line. And remember the volume of solid of revolution using disk method, it was basically if you rotate your function about the x-axis, you're looking at the cross-section, which is a circular region or a disk, and the volume is pi, the definite integral from a to b of f of x to the second power dx. Why is that? Remember that the cross-section is a disk or circular, solid circular region, and a is pi r squared. So in this case, get pi f of x to the second power, and then you take the definite integral with respect to x. This is our disk method. We talked about shell method as well. Now let us just review the washer method. For the washer method, here you have two functions that you have a region bounded between two functions, and then the cross-section is similar to a washer. So you're basically finding the larger area, finding the smaller area, and you do the subtraction. The volume is basically saying that, hey, it is the larger area minus the smaller area, definite integral with respect to x. If you're rotating this along x-axis. And when you're rotating this along y-axis, well, you convert everything into y. So the y-axis, as you can see, the cross-section or washer spot, it's rotated about y-axis. So in that case, the volume can be calculated of pi r of y to the second power minus r of y to the second power. And here, r of y is basically the larger radius, and this guy here, r of y, with small r, is the smaller radius or inner radius.